Okay, dokie. Big O notation. Just as a notation in math, describes a like limiting behavior or function, or if it tends to a certain particular value. But in computer science, to me, it just kind of means how efficient your functions and algorithms are with when you're given an input, like how many steps or calculations does it need to be. So, like the first one is like big O, or just constant time, big O of one. So what would happen is no matter how big your uh, input is, could be a list of just the biggest numbers. So you can like, let's see here, return list, return first. You could do like 1, 2, 3, 4, 5, 6, 7, or 5, whatever. It's still gonna just print out the first one. So it's gonna be one, and if you change, well, you get the picture. You know, so it's just gonna be always super quick. And then the next one is like typically with functions is linear time. So it's big O of n. So it means it just scales relative appropriately, step with step, with just how big your input is. Your input, this, so it's gonna take this long because there's 5 elements. So it's gonna pick up 5 elements. If there's a million elements, it'd take a million. If there's sextillion elements, then that would be take forever. So that just scales 1 to 1 kind of. And then quadratic time, big O of n squared is when it squares at a quadratic rate. So this where it steeps into gets, you got to be careful. If your inputs get too big, it can take a little bit longer, slightly. So this one, I made a function that prints out all the combinations you can make with a list of elements. So you can see here, if that's how we go. And it returns all the combinations. You can see there's how many there, 1, 2, 3, 4, 5, 6, 7, 8. Well, it'll just be like how many there? 16. And it shows that there's 16 calculations or steps that we made in this function. So, but then if we do something a lot longer, it's going to take a little bit longer. See? And in this case, it took 121, so it's probably 11 elements in there. But just say you have a list of like 1,000, so whatever 1,000 squared is, so that'd be like a million. It has to take a million steps, so that'd take a little bit longer. And then the king daddy of them all is exponential time of big O. So that's when your factor is an exponent. So a illustration of this would be just doing a Fibonacci. This is a Fibonacci function. So it just takes what element, the nth element in a Fibonacci sequence. So if you just do just say 4, this would be relatively quick here. Just be 3. Now let's just stack it up to like 15. It should take a little bit longer here. Oh, that's pretty quick. But let's get up to 34. Now this is where it gets big and hairy. So see, it's taking a longer time here to calculate the 34th element in the Fibonacci sequence. So, which is apparently 5,702,887. But yeah, essentially what this does though is it always recurses. It uses recursion, so it always recurses back. So I won't get into the math. It's not like, apparently it's like the golden ratio is like 1.6 something. But like that's what this was what it would scale at. So that's the big O. It's not 2, but still, nonetheless, the variable is in the exponent. So, yeah, so that's big O notation, a quick jiffy explanation of it, and I don't know how often it is used in day-to-day web development, but I suppose in big data sets and then very heavily computational, like game development, graphics and stuff, it might be a little bit more important. But anywho, That's how much I know at this time.